3.1 Exponential Functions. So an exponential function is something of the form f of x equals a times b to the x power, where my base is b. The x, the exponent, is any real number. Let's see, a and b have to be real number constants. A cannot be 0. B is positive. And b is not equal to 1. So kind of lots of different clauses there. We have to have everything exactly right, but then an exponential function is that form. So the key for an exponential function is the exponent is the variable. So I don't have x to a power, I have something to the x power instead, raised to the x power instead. So examples would be like f of x equals 4 raised to the x power. So my x is my exponent. Or f of x equals -2 times, and so the -2 would be like a times 1/3 raised to the x power. So my base is 1/3, my exponent is my x again. Non-examples would be f of x equals x squared, because my variable is not my exponent, and f of x equals 1 to the x power, because we say up here that b can't equal 1, and that's because it doesn't matter what power I raise 1 to, it's still 1. So that really would be a constant function. So for example 1, we're going to just work on graphing, and then we're going to go through and analyze our graphs. So I'm going to make a table. When I'm using exponential functions, I can substitute negative numbers and 0 and positive numbers. So I'm going to see all the different things that happen. 4 raised to the -2 power would be 1 over 4 squared, or 1/16. 4 to the negative first raised to the negative first power would be 1/4. Anything raised to 0 power is 1. 4 to the first is 4, and then 16. So let's go through and graph that. Let's go through and make a straight line and graph that. So let's see. I need to have maybe 1 and 2 on here. All right. So when I have 0, there's 1. 1 is 4. -1 is 1/4 already. So that looks pretty good. We can't actually put very many of those points on the graph. And then it looks like I have an asymptote here. I can see how as I keep raising the 4 to to smaller and smaller exponents, smaller like -3, -4, -5, I'm going to get closer and closer to 0, but I won't quite reach 0. So let's go through now and just analyze our function. So our domain is going to be all real numbers, right? We stretch from -infinity to +infinity on our x-axis. X can be anything. So we're going to write that in interval notation. Our range, though, we can see that our graph is nowhere below the x-axis. So our graph is going for the y direction from 0 to +infinity. And we're not really equaling 0, we're just close to it, so it's going to be a soft parenthesis at 0. So from 0 to infinity for range. When I look at my x-intercept, there are none. So there actually aren't any to look at. My y-intercept is 1. And you could see with these kind of functions, if I raise anything to the 0 power, I'm going to get 1. My function is increasing for the entire function. So increasing on -infinity to infinity. And I can see that I have an asymptote, so I'm going to go ahead and write that down. My asymptote would be y equals 0. And then when I am thinking about my end behavior, as x goes to -infinity, my y, my f of x, gets closer and closer to 0, because that's my asymptote. As x goes to positive infinity, though, that's where I keep raising it to an exponent and I get a bigger and bigger and bigger number. F of x is going to go to, I wanted to have an arrow here, positive infinity. So now we're going to look at something raised to a negative exponent. So we'll use the same, let's just use -1, 0, 1, because I can already tell if I square 5, really big number, not going to work. So if I have 5 to the negative, raised to the negative of -1, that'll just be 5 to the first. This is going to be 5. This is always 1. 5 to the raised to the -1 power would be 1/5. And then I'm going to go ahead and graph it. So this time, 1, 2, 3, 4, 5. -1 is 5, 0 is 1, 1 is 1/5. Right, and asymptote right here again. I can see it after I graph that I'm going to get closer and closer to 0, but I'm never actually going to equal 0. So my domain again is from -infinity to infinity. My range again, a lot of these are the same. I don't think we're going to bother with doing this over again. But one thing I do want to say is that my first graph is exponential growth. So let's add that in. This is exponential growth. Exponential growth. Because my base is greater than 1. And the other thing that we worry about is if we have a coefficient that needs to be positive. We can't have a negative coefficient or anything. That wouldn't give us exponential growth. That would flip it over the x-axis. The second one might look like exponential decay, but it's not. Exponential decay is going to be when I have a base that's like 1/2 or 1/3 or something. We're not going to get exponential decay by just having that negative exponent. So here is kind of a breakdown of growth and decay. So again, in order to have exponential decay, our base has to be between 0 and 1. And then on this one, to have growth, our base has to be greater than 1. So that's kind of what we just talked about. You can see exponential growth, the function's going up from left to right. It keeps getting bigger. You can see it's growing, and the decay does the opposite. And then here we kind of broke down all the different domain range and behavior continuity. So this transformation should be review as well. Vertical transformations, we know we get that by adding numbers after a function. So if it says a plus c, that means we go up c units. If it says minus c, we go down c units. So that's just review. If those numbers are instead with the x, we know that they do the opposite in the x direction. So if it says plus c, that's going to be left c units. So instead of positive in the x direction, it moves it to the left. And if it says a minus c, then it's really going to shift it to the right. So everything that's with the x always ends up doing the opposite of what we think. So this negative outside we know is going to reflect about the x-axis, or in the x-axis we usually say, and we knew that already. And it turns out if I have a negative with my x instead, that one's going to reflect over the y-axis, and that's the kind of graph we just looked at a second ago. So you could see with these first graphs, this one goes up from left to right and make my exponent negative, and now it's flipped over the y-axis and it's going down instead. When I have a vertical stretch or shrink, that's this number multiplied in front of my function. And if the number is greater than 1, I'm going to stretch it. If it's between 0 and 1, it's going to shrink it. So that, again, would work just like a parabola or anything else that we've worked with in the past. So it's always good to have good graphing skills for parabolas because everything else is the same. So I wanted to add in here, because I took this from your book, but the book says nothing about horizontal stretching or shrinking. So let's go ahead and add that. And horizontal, we know, is always going to have to affect the x. So I'm going to make this g of x equals b to the cx power. So now I'm affecting the x. And that is going to stretch now, and this one's reversed from the y numbers. So this time we're going to stretch if it's between 0 and 1. And we're going to shrink if it's greater than 1. So remember, it's always doing the inverse. So if I have a 2x, I'm really dividing by 2. If I have a 1/2 x, I'm really multiplying by 2. So it goes right along with that pattern where x's kind of always do the opposite of what we think. And then just so it looks like the other ones, I'm going to go over the C here and stretch and shrink and just kind of underline main ideas. So now we're going to take a look at the graph of 1/2 raised to the x power, and then look at how these functions would change depending on what we do. So if we have, and I'm going to move all this stuff down because I want room for that original graph. So if we have this graph, 1/2 to the x power, let's think about what our original function would look like. So I would have an x and a y, -2, -1, 0, 1, 2. If I raise something to a negative exponent, it's going to flip it and then square it. So we'd have 4, 2, anything to the 0 power is 1, 1/2 raised to the first power is 1/2, and then 1/4. And then let's look at how our graph is. So -2, and I'm making this graph pretty small because I want to just be able to refer back to it. So -2 is 4. -1 is 2. And this is going to be exponential decay because my base is between 0 and 1. And my 0 is 1, and then my 1 is down to a 1/2, and then a 1/4. So my graph is going to look something like this. This is really super messy because we're trying to fit it in here. So now when I look at this x plus 1 for my exponent, we know that it's going to move it 1 unit in the x direction. It's going to go the opposite. So this is going to be 1 unit left. So I am going to simply take my table and my graph from up above, and I'm going to shift everything 1 unit left. When I look at this one, I have a negative on my exponent, so we know that that one is going to reflect in the y-axis, or about the y-axis. So it's going to be really easy for me to take these graphs now and change according to those directions. So here's my axes, and now I know I'm moving everything over. So instead of -2, 4, it's going to be -3, 4, and then -2, 2, and then -1, 1, and then 0 is now the 1/2, and 1 is now the 1/4. And I still have that asymptote. And when I look at this one, I know it will be reflected about my y-axis. So the 0, 1 is still going to be there, but now I'll have 1, 2, and 2, 4, -1, 1/2, -2, 1/4. So my graph will look like this. And again, we have that y-asymptote. I think it's good for our brains to kind of draw it and to remember it's there, but I don't think that's really a necessary step of drawing. So one more of these functions. This time I have a -2 multiplied by the entire function. So I know that this is going to reflect in the x-axis, or over the x-axis, or about the x-axis. And then the 2 is going to be a vertical stretch. So for this one, it's a couple more steps. I could probably just figure it out, but I think it would be smart if I made a table. So first I'm going to list down my normal x values that I had on the other page for my table, and I'm going to look at just 1/2 to the x power raised to the x power, which I already did. So I know this was 4, 2, 1, 1/2, and 1/4. And now I want to look at if I took all those numbers and I multiplied them by -2. So I'm kind of doing a three-way table, where first I did my normal function. Now I'm taking all my y values and multiplying them by -2. All right, now I know that this row in between is not really the row I need. That's for my original function. So I'm going to use these for my x's. And I'm going to use the last row, which is what my function actually is, for my y's. And I'm going to go ahead and graph. And hopefully I can make the scale go down to -8. All right, so -2 is -8. And I think I'm going to use a new color for this. -1 is -4. 0 is -2. 1 is -1. And 2 is -1/2. So I still have, throughout everything I've done, unless I shift it up, I'm going to always have that asymptote right at 0. I'd have to have like a plus or a minus out at the end to move that, and that would move my asymptote as well. So here's some different formulas for interest. So the P is always our initial amount, and then depending on the rate, the interest rate we get, and the amount of time, or N, the amount of time that we're compounding per year, that's going to change how much money we get out. So that A of T is going to be the money that we get out when we invest. So we've got just compounded annually. I never memorize the annually one because you can get it just by putting 1 in for N's. So we do need to know this formula here, though. Oh, I didn't circle the NT, so let's go back and fix that. So you do need to know both of these. And this one I could just remember from the word PERT. I know that was a shampoo brand a long time ago, so that helps me remember that. Here's the formula again. Don't know why we have that page on there. So here is just going to guide us through what's going on. So we have $2,000. That's going to be our initial investment. So A equals 2,000. We have a 5% interest rate. So R equals 0.05. Make sure you change it to a decimal. And we're talking about after 18 years. So T equals 18. And let's just do a quick reminder that our formulas are this one, A equals P. I usually do P for the principal. I think that we'd have a different formula here. No, we did it that way. Okay, good. A equals P times 1 plus R over N to the NT power. The second one is A equals PERT. So for quarterly, that's going to be 4 times a year. So N is going to equal 4. Monthly means 12 times per year, so N will equal 12. Daily, we're going to assume is 365 times per year, so N equals 365. And continuously means we're going to use that PERT formula. So let's go ahead and look at A. I'm going to write down my formula and substitute all my variables. A equals P. I don't know why I wrote down P there, or A instead. So A is going to be 2,000. That's my initial amount, times 1 plus my rate is 0.05, 4 times per year to the NT power, so 4 times 18. And you really need to be careful about order of operations when you plug it into your calculator. You should come up with $4,891.84. So this is more of like a make sure you can get the correct answer kind of check. For B, I am using almost the same formula, but I'm compounding more. So I'm expecting to earn a little bit more money. So 0.05 divided by 12 to the 12 times 18 power. So for B, you should get, and go ahead and pause this and try it on your own, $4,910.02. For C, and we'll do the same steps again where I'm going to plug it in and then give you the answer. Should be 2,000 times 1 plus 0.05 divided by 365 raised to the 365 times 18 power. And then for D, continuously, I'll have A equals 2,000 times E raised to the 0.05 times 18 power. And so continuously is going to be the most money of all. So this should be $4,910.02. You know what? I didn't tell you the total on C, did I? And I got B wrong. So let's fix this really fast. All right. writing these things down and then copied the wrong ones over. Okay, so for D, which I was already on, should be $4,919.21. And then for C, you should have had $4,918.90. So please make sure that you can use your calculator and figure it out. A lot of times I find that for me, I have to do order of operations. So I would, for example, plug in the 0.05 divided by 365, divide that out, and then I would add my 1, and then I would raise it to this power, and I'd have to put parentheses around that to make sure it raised it to the entire power, and then I would multiply it by 2,000. So for me, that's what I find the best. And I'm happy to show you with a calculator underneath the document camera so we can work on getting those same answers. It's really frustrating to be able to set up a formula, but then not be able to get the right answer. That is it for our 3-1 notes.